are the data indexing team, and the indexing structure that we are going to use is arteries, and these are the members of our team. First, let me give you an overview about arteries. Arteries are similar to B+ trees. They consist of a root, they consist of internal nodes and leaf nodes. The root holds the pointer reference to the largest region. As you can see over here, T and U are the root nodes, and they hold the reference to the largest regions in the entire artery. The internal nodes hierarchically store pointers to their child nodes, storing data bounded within the parent's area. As you can see, N, P, Q and RS are the internal nodes. The leaf nodes will store the actual data within respective MBR. So the leaf nodes that you see here, these are the actual rectangles stored within the artery. What is an MBR? An MBR is a minimum bounding region. So this is basically a sub-region within the entire space that group data as efficiently as possible, and in a way that the area used is as small as possible. Now we are going to talk about the insertion in an artery. Insertion of artery is similar to B+ tree. We'll first talk about an example where there's a simple insert, meaning that the object will automatically fit into an existing MBR and there is no need to change the size of the MBR. So we're going to insert object X into the artery. This is the existing artery, and we need to insert X in it. As you can see, X can automatically fit into this green artery, green MBR. Next is an insertion when MBR needs augmenting. So over here we are inserting object X into the artery. As you can see, the MBR ends over here. So in order to fit X into the MBR, we need to augment the MBR and make it larger so that X can also be covered. This is a second type of insertion. Third is when we need to partition the box. Here X needs to be inserted. As you can see, this particular MBR can be split into two MBRs, BB1 and BB2, and X can be incorporated into this MBR. For the search algorithm, the input is going to be the root node and the region within which we want to find rectangles. So it is going to search all the non-leaf nodes. As you can see, if the node is not a leaf node, then you examine each entry of the root node, so each child of that root node, and find the MBR which will intersect with the bounding box Q. And then for each such entry that satisfies that condition, we're going to perform a range search. So that is basically going to recursively call this algorithm again till it finds the smallest MBR, which results in the intersection of the region given. For implementing the artery algorithm, we use Boost, which is a C++ library. The header files or the important files which we use from Boost are geometry.hpp, point.hpp, box.hpp, and artery.hpp. Let's go over the classes that are used in data partitioning indexing. Our primary class is the data indexing wrapper class. This class inherits the spatial index interface class and overrides all the functions of spatial index interface. This wrapper class contains the point data index and rectangle data index class objects. Point data index and rectangle data index handle the indexing logic. Let's look at the point data and rectangle data index classes. Point data index class has an object of type artery called artery object. An instance of this object is going to store the actual artery that gets generated. Similar is the case for rectangle data index as well. The fan out of the artery is going to be 16. Now let's look at the create index function. What the create index function does is takes a collection of points as input and uses the getNext function of class point collection to extract the points within the collection and then inserts them into the artery one by one by converting them into the boost point type. Similarly, for the rectangle indexing, it takes a collection of rectangles, converts them into a box and inserts them into the artery. Now let's look at the search function. The search point function takes as input a rectangle or a bounding box. Now this search function will return all the points that are intersecting or are within or are overlapping the given boundary. This is taken care of by the intersects query of artery given by the boost library. The result of this query is stored in the query result vector, and this result is then converted into a point collection, and this point collection is returned back to the object that is calling this function. Now we're going to talk a little bit about the search function for rectangles. For a bounding box, the search function for rectangles should return the rectangles within the box and also the rectangles that are overlapping or intersecting the boundary. The boost library does not have an explicit query for these specific requirements. Therefore, we implement two separate queries. One is overlaps. This query will return just the rectangles that are intersecting the boundary, as you can see, and covered by. This query is going to return the rectangles that are entirely inside the boundary provided. And then we take the union of these results. So the first query is covered by. The results of that are going to be stored in result underscore covered. The second query is overlaps, and the result for that is going to be stored in result underscore s. And the final is result final. So we take the union of the two previous query results and then store it into result final and return that back to the user. These are some of the results that we calculated based on normal insertion and insertion using the packing algorithm. And the splitting algorithms that we used were linear, quadratic, and R star for different fan outs. As you can see, the linear algorithm is the best algorithm for both kinds of insertion, and the insertion time for packing algorithm is of the order of 0.6 to 0.9 seconds, whereas for the normal insertion it goes up to 30 seconds. So clearly the packing algorithm is the best algorithm. When it comes to the fan out, we believe that 16 is the most appropriate fan out and it gives the best results. Similarly, the results for rectangles are also the same. Packing algorithm performs significantly better as compared to the normal insertion method, which is why we have used packing algorithm in our final code. Similarly, these are the graphs for the search query results. As you can see, the linear algorithm generally gives good performance consistently for points, and for rectangles, the linear and quadratic algorithms both give good performance, and R star algorithm generally gives an inconsistent performance. we conclude by saying that the creation time for R trees is more, but it gives good lookup performance and searches really quickly. The memory utilization in R tree is minimal. Each MBR only stores the pointer to all of its child nodes, and each leaf node only stores the x and y coordinates of the geometry that it stores in float data type.